So how do you teach a machine to be creative? Your first instinct is probably to give it a goal, right? A target to aim for. But what if we did the exact opposite? What if we built an AI and its only instruction was, do something new? Anything, as long as it's never been done before. This is the wild world of goal-free AI, and we're about to dive in.
Okay, so take a look at this robotic arm. It's from this experiment where its job is not to put that block in any specific spot. Instead, it gets rewarded just for moving the block to a new position. Any new position, every single time. It's this fascinating paradox, isn't it? How can you possibly get good at something when the target is always moving?
And that really gets us to the heart of what we're talking about today. What actually happens when an AI's one and only goal is just to be new? Well, the answer is wrapped up in this really powerful idea called divergent search. It's a method for training machines to find solutions we would have never even thought to look for.
So, let's break this down. Divergent search is basically a whole family of algorithms that, as the paper we're looking at puts it, are all about abandoning objectives altogether and solely pursuing behavioral novelty instead. I mean, that's a pretty radical idea compared to how we usually think about training AI. The core concept is actually surprisingly simple. In normal AI training, you get a little reward every time you get closer to the right answer. But with this method, the AI gets its reward for doing something different, like moving that block to a spot that its friends, or even its ancestors have never been to before.
Right, but this brings up a really important question. If you're constantly moving the goalposts, how does an AI ever actually improve? I mean, how does it build a real capacity for innovation instead of just, flailing around randomly? Well, it turns out there's a secret ingredient.
And that secret ingredient, that secret sauce, is something called evolvability. And this isn't just about coming up with one new idea. No, it's about having the built-in ability to generate tons of different creative solutions way down the line. It's basically the engine that drives open-ended creativity. The source material gives us this really solid definition. Evolvability is the capacity of a solution's internal code, they call that the genotype, to produce offspring that have a huge range of different behaviors, or phenotypes. So in simple terms, it's a measure of pure creative potential.
Now, to really get this, we got to understand the difference between genotype and phenotype. The genotype, that's like the AI's blueprint. It's all the code, the weights in the neural network. The phenotype is what the AI actually does with that blueprint, the final position of that block on the table. So evolvability is all about how tiny little tweaks to the blueprint can cause this big, beautiful explosion of different final actions.
A really great way to picture this is to imagine all the possible things the robot could do, every single spot it could put that block, as this enormous landscape. An AI with high evolvability isn't just good at taking one little step, it's amazing at producing offspring that can jump to completely different corners of that map, exploring the full range of what's even possible.
Okay, so if evolvability is the thing we want, how do we get more of it? Well, the researchers ran a bunch of experiments to figure this out, and they were really focused on two main questions.
So their first big question was this. If you actively select for novelty, what they call evolutionary pressure, does that actually make the AI more evolvable in the long run, or does it just kind of make it do weird stuff for a while before it gets stuck in a rut?
And the results were, they were incredibly clear. As you can see right here, with zero pressure, just a random search, the evolvability actually went down over time. But the more pressure they put on, the more they selected for only the most novel solutions, the higher and higher that evolvability climbed. The pressure to be different literally forces the AI to get better at generating difference.
And this wasn't just some vague feeling they had. The data showed a really strong, statistically significant positive correlation. That number you see, R equals 0.71, that's the hard evidence. It proves that pushing for novelty is a direct way to train an AI to become more creative and better at exploring in the future.
So this brought them to their second big question. Does the way you measure novelty actually matter? I mean, is being novel just about being a little different from the guy next to you, or is it something more than that?
And what they found here was super interesting. The best way to measure novelty wasn't just to check how far away you were from a few neighbors. Instead, a more sophisticated method that looked at the overall density of the whole explored area worked way better. To put it simply, it rewarded the AI for finding truly uncharted territory, these empty parts of the behavior map, not just for wiggling around in an already crowded spot.
Now, building on all these discoveries, the paper makes what I think is its biggest contribution. It proposes a totally new, much more powerful way to even think about evolutionability itself. They basically argue that our current definitions are a little short-sighted.
The paper says that the standard definition of evolvability is, and this is a quote, myopic. It's myopic because it only looks one generation ahead. It can tell you if a parent can create diverse kids, but it completely ignores one giant, crucial question.
What if those diverse children have zero creative potential of their own? You see the problem. A solution might look really evolvable because it spits out a whole bunch of different offspring, but if none of those offspring can innovate any further, it's just a flash in the pan. It's an evolutionary dead end. So the paper lays out this long-sighted approach. First, you map out that whole landscape of all possible behaviors into different regions. Second, you figure out the odds of jumping from any one region to any other. And finally, and this is the key, you calculate a solution's true value, not by its immediate kids, but by its long-term potential to unlock all the other regions on the map, many generations down the line.
And this leads to my absolute favorite analogy from the paper. They say some solutions aren't just stepping stones, they're wormholes. They're these very special solutions that have a unique talent for producing offspring in remote, almost unreachable parts of the behavior landscape, completely blowing open new paths for exploration that were locked before.
Okay, so we've been way down in the theoretical weeds here, but let's pull back up for a second. Why does any of this actually matter? Why do we even need an AI that can just explore without a goal?
Well, this kind of AI is an absolute game changer for problems where the rewards are really rare, or where the obvious path is actually a trap. It lets us generate not just one good solution, but a whole library of different, high-quality options for any given problem. Ultimately, it helps us build systems that are way more robust and adaptive by, as the paper says, illuminating the entire universe of what's possible, not just the one single thing we thought we wanted at the start. And that really is the biggest takeaway here. This research points to a massive shift in how we think. Instead of training an AI to find a needle in a haystack, we can train it to just get really good at searching the haystack. But rewarding creativity for its own sake, we're giving our machines the power to not just find one answer, but to map out entire universes of solutions we never even knew existed.
So I'll just leave you with this to think about. If a machine can learn to be creative with no objective at all, what impossible problems in medicine, in engineering, in art, could we finally solve just by telling our most powerful tools not what to achieve, but simply to explore?